Let's continue to read the book Until the End of Time by Brian Greene. This is chapter 3, Origins and Entropy, from Creation to Structure. When mathematics allows scientists to peer back to within a fraction of a second of what may well have been the beginning of the universe, the proximity to traditionally religious terrain suggests to some that there is a deep alliance or a deep connection or a deep conflict straining to be revealed. It's why I receive inquiries about my views on a creator almost as frequently as those asking about science. Indeed, questions often straddle the two. We will have ample time to consider such matters in later chapters, but here we will explore one point of contact, raised at the end of the previous chapter, essential to our larger story. If the second law of thermodynamics burdens the universe with a relentless increase in disorder, how can nature so readily produce the exquisitely configured, highly ordered structures, from atoms and molecules to stars and galaxies, to life and mind? If the universe began with an explosive bang, how could that theory unfolding have given rise to all the organization, from the swirling arms of the Milky Way to Earth's stunning landscapes, to the intricate connections and corrugated folds of the human brain, to the art, music, poetry, literature, and science such as brains produce? One response relied upon through the ages to address embryonic versions of such concerns is that order is hewn from the chaos by a supreme intelligence. Human experience aligns with this anthropomorphically inspired term. After all, much of the order we daily encounter in modern civilization is the handiwork of intelligence, but a proper exegesis of the second law renders an intelligent designer unnecessary. As surprising as it is remarkable, regions containing concentrated energy and order, stars being the archetypal example, are a natural consequence of the universe diligently towing the second law's line and becoming ever more disordered. Indeed, such pockets of order prove to be catalysts that facilitate the universe over the long run to reach its entropic potential. Along the way, and as part of this entropic progression, they also facilitated the emergence of life. To explore the dance between order and disorder playing out across cosmological history, we begin at the beginning. Next section, sketching the Big Bang. In the mid-1920s, Jesuit priest Georges Lemaitre used Einstein's newly minted description of gravity, the general theory of relativity, to develop the radical idea of a cosmos that began with a bang and has been expanding ever since. Lemaitre was no armchair physicist. He received his doctorate from the Massachusetts Institute of Technology and was among the first scientists to apply the equations of general relativity to the cosmos as a whole. Einstein's intuition, which had successfully guided him through an exquisite decade of discoveries into the nature of space, time, and matter, was that objects in the universe have a beginning, middle, and an end, but the universe itself always was and would always be. When Lemaitre's analysis of Einstein's equations suggested otherwise, Einstein dismissed him out of hand, telling the young researcher, "Your calculations are correct, but your physics is abominable." Einstein was emphasizing that you can be adept at manipulating equations and yet lack the good scientific taste to decide which of those mathematical manipulations reflect reality. A few years later, Einstein performed one of the most famous scientific turnabouts. Detailed observations by the astronomer Edward Hubble, working at the Mount Wilson Observatory, revealed that distant galaxies are all on the move. They are still rushing away, and the pattern of their exodus, the farther the galaxy, the higher the speed, agreed with the mathematical output of general relativity's equations. With data now supporting Lemaitre's abominable physics, Einstein embraced wholeheartedly the conception of a universe that had a beginning. In the century since Lemaitre's innovative calculations, the cosmological theorizing he initiated, together with independent work by the Russian physicist Alexander Friedmann, has been substantially developed, and a corpus of observational evidence from ground and space-borne telescopes has been amassed. Here is the modern cosmological account that has emerged. Some 14 billion years ago, the entire observable universe, all that we can see, using the most powerful telescopes imaginable, was compressed into a stupendously hot, incredible dense nugget, which then rapidly expanded. Cooling as it swelled, particles gradually slowed their frenzied motion and aggregated into clumps, which over time formed stars, planets, all manner of gaseous and rocky debris scattered across space and us. In 2 sentences, that's the story. Let's refine it. Let's examine how, without intent or design, without forethought or judgment, without planning or deliberation, the cosmos yield meticulously ordered configurations of particles, from atoms to stars to life. Let's understand how the emergence of such ordered structures squares with the second law's decree of a relentlessly increasing disorder. Let's witness the entropic two-step now performed on the cosmological stage. To that end, we will need to understand various cosmological details more fully. First up, what drove the primordial nugget to start expanding in the first place? Or, in looser language, what ignited the Big Bang? Next section, repulsive gravity. Antonyms abound because experience is full of opposite. Physics, too, has its share. Order and disorder, matter and antimatter, positive and negative. But since the time of Newton, the force of gravity appeared to stand apart from this common pattern. Unlike the electromagnetic force, which can push or pull, gravity seemed to be solely an attractive force. According to Newton, gravity exerts a pull between objects, whether particles or planets, that draws them together, but never the reverse. Absent a principle that requires symmetry in all of nature's workings, most who thought deeply about gravity viewed its one-way character as an intrinsic quality that simply had to be accepted. Einstein changed this. According to the general theory of relativity, the gravitational force can be repulsive. Newton did not anticipate repulsive gravity, and neither you nor I have ever experienced it. But repulsive gravity does just what the name suggests. Instead of pulling inward, it pushes outward. According to Einstein's equations, big, clumsy things like stars and planets exert the usual attractive version of gravity, but there are exotic situations in which the gravitational force can drive things apart. While the capacity of the gravitational force to be repulsive was known to Einstein, as well as a number of subsequent scientists who worked on the general theory of relativity, its most profound application took more than half a century to be discovered. As a young postdoctoral fellow contemplating the Big Bang, Alan Guth realized that repulsive gravity might address a confounding cosmic mystery. Observations revealed that space is expanding. Einstein's equation concur. But the equations remained mute on the question of what force, billions of years ago, set the expansion off and running. Guth's detailed mathematical analysis, culminating with a late-night calculation frenzy in December 1979, coaxed the equations to speak. Guth realized that if a region of space was filled with a particular kind of a substance, something I like to call cosmic field, and if the energy contained in the cosmic field was spread evenly throughout the region, not clumped like a star or planet, then the resulting gravitational force would indeed be repulsive. More precisely, Guth's calculation revealed that if a tiny region, perhaps as small as billions of a meter across, was suffused with a certain type of energy field called the inflation field, with the missing I, being an intentional, if a quirky naming convention, and if the energy was distributed uniformly, like a steam whose density is the same throughout a sauna, the repulsive gravitational push would be so forceful that the speck of space would inflate explosively, almost instantaneously, stretching to as large as the observable universe, if not far larger. Repulsive gravity would thus power a bang, and a big bang at that. In the early 1980s, Soviet physicist Angie Linde and the American duo Paul Steinhardt and Andreas Albright took Guth's hand off and ran with the concept, developing the first fully viable versions of the inflationary cosmology. In the decades since, these early works have inspired thousands of pages of intricate mathematical calculations and a great many detailed computer simulations, filling journals worldwide with explanations and predictions based on the assumption of an inflationary past. Many of these predictions have now been confirmed by painstakingly precise astronomical measurements. While I won't lead you on a full tour of the observational case for inflationary cosmology, something amply covered in many articles and books, I will describe one success that many physicists consider the most compelling of all. It is also the feature we will need for the next step in the cosmic unfolding, the formation of stars and galaxies. Let me stop here and read it next time.